Okay, so thanks for coming, everyone. Our speaker today is Aziza Suleymanzade from the University of Chicago. Aziza did her undergrad work at Harvard, where she graduated cum laude in physics. And after that, she went to the University of Cambridge for her master's degree, where she worked as a Lionel de Jersey Harvard Cambridge scholar in Zoran Hadzibabich's lab on working on ultra cold atom experiments for trapping potassium 39. And now Aziza is finishing up her PhD at the University of Chicago, where she works with John Simon and David Schuster on engineering strong interactions between optical and millimeter wave photons using Rydberg atoms. Yeah, thanks so much for being here today, Aziza. Looking forward to your talk. And for questions, people can put their questions in the chat box, and I can read them to Aziza if you have them during the talk, or you can save them for the end. Or Aziza also mentioned she might pause at some natural stopping points in her talk for questions, but you also can unmute yourself and ask questions yourself, whatever people prefer. So yeah, Aziza, take it away.
All right, thanks, Anita, for the nice introduction. I am gonna go ahead. Okay, so today I'd like to tell you about our work on millimeter wave photons for quantum science and technology. I will talk about our hybrid setup and how we use millimeter wave frequencies successfully for that work, and how the hybrid experiment that I've been working on mostly have led me to explore millimeter wave band beyond cold atoms and cavity QED systems. Okay, so before I go into my research and our work at U Chicago, let's get to know millimeter wave frequencies a bit more. So they are not very popular in quantum science yet, but it's changing, and science at Stanford is a good indicator of that. So millimeter wave frequencies lie in the electromagnetic spectrum between microwave and infrared regimes. Usually we identify them as having frequencies between 30 and 300 gigahertz and having wavelengths of 1 to 10 millimeters. So even though they're not yet very widespread in quantum technology, they have a wide scope of applications outside of physics. So for example, in chemistry, due to abundance of vibrational and rotational resonances, chemists use millimeter wave spectroscopy to study molecules and molecular crystals. On the other hand, in medicine, due to the fact that millimeter waves in comparison to microwaves give higher resolution, and they're used in cancer diagnostic and imaging. So they're also very important in astrophysics. So our atmosphere has transparency window around 1 millimeter, even though there is some absorption there, which means that the astrophysicists who are trying to measure these frequencies have to build their telescopes in a high altitude and dry areas. So as I mentioned, a lot of molecules have vibrational and rotational states at 100 gigahertz. This means that they're really widely used in astrochemistry. So there's a lot of detecting of molecular traces around the galaxies and stellar bodies, and through that studying their evolution and dynamics. I don't know if you guys were following, but recently there was a discovery of phosphine gas around Venus, which in media was and translated into a possible sign of life. But so the discovery of phosphine on Venus was actually done using the data from millimeter wave telescopes, both in Chile and Hawaii. And the scientists say that this discovery either means that there is some chemistry we still don't understand that leads to phosphine in Venus, or there is a possibility of a sign of life at some point of time around the planet that we didn't think that had such characteristics. Another place where millimeter wave frequencies are detected for astrophysics is South Pole. It's a dry, high elevated area, and millimeter waves being a prominent signal coming from CMB, cosmic microwave background, because cosmic microwave background is at 2.7 Kelvin. Scientists at South Pole Telescope try to detect these faint signals to study the universe a few seconds after the Big Bang. In fact, astronomers go even further, and they build their telescopes using cryogenic circuitry in order to be able to push towards quantum limited detection and being able to detect really very faint signals by lowering the thermal background of the detector. So before COVID, we used to travel, and most of you have passed through TSA and through this detector, which is actually a millimeter wave device. So by shining millimeter waves through, it tells TSA agent if you're wearing any metallic objects that really well reflect millimeter wave frequencies. And finally, the field that has made the biggest contribution to millimeter waves recently is telecom. So communication companies have made millimeter wave band a new frontier. This lowest row of frequency allocation, that's crazy busy right now, recently has gone through a billions of dollars bidding war for some of the frequency bands. And the reason is because as connectivity becomes a big part of our lives, and not just science and technology, we're realizing that we're running out of bandwidth in 4G and LTE. So telecom companies really have started pushing towards higher frequencies in order to get more bandwidth and low latency. So this popularized 5G is potentially enabling this technology using millimeter waves by going into high frequency, and promises not only faster communication, but also things like remote surgery, smart cities, self-driving cars, and so much more. So of course, the question is, why do we care, or why do I care? Well, this buzz and progress in many other fields using millimeter waves made the devices, the technology at millimeter waves much more accessible. There are more companies making cables, detectors, sources, and waveguides, and these companies are getting bigger and more responsive to, sad grad students who really need their connectors to arrive. So with that overview, I would like to now come to my field of expertise and really pin down on why millimeter wave frequencies could be useful in our field and in quantum devices and quantum technology. So it is not very well explored, even though there have been some pioneering works starting in the 80s and well up to 2000s by Hirosh, Rempe, and others in high frequency microwave masers and entanglement, which basically revolutionized the field of quantum technology and jump-started the field of Rydberg cavity QED and eventually circuit QED. But since then, the field has been relatively quiet, but I think it's changing. And as I mentioned before, research at Stanford is a good indication of that change. The millimeter wave band is promising for quantum technology, and for many reasons. So let's start from temperature. At 7 Kelvin, there are less than one thermal photon at 100 gigahertz. At 1 Kelvin, there's almost zero. This means that reaching quantum regime or zero thermal background, zero thermal photon background with millimeter waves only requires modest cryogenic temperatures. So this is exciting because it could drastically reduce the cost of quantum systems, get rid of dill fridges, which use helium, and helium is a non-renewable source and it's depleting and expensive. And potentially could democratize quantum science, making it more widely available. And on the other hand, progress in quantum technology at millimeter wave frequencies could also benefit the other fields that I've mentioned. For example, a quantum detection at 100 gigahertz could really help and bring astronomy closer towards quantum limited detection. Then there's the fact that the quantum platform that we use now already have an abundance of emitters at 100 gigahertz. So, we have spin defects, optomechanical membranes called molecules and atoms, and even superconducting circuits. This not only means that there's already a wide range of qubits we could use for quantum technology, but also means that we could really benefit from hybrid systems that utilize millimeter wave technology as one of the platforms. And finally, the fact that millimeter waves have such an intermediate length and energy scale means that the devices can be machined and fabricated, and both the ray optics and near field electromagnetic tools can be applied to shape and manipulate photons. So we can use tools from electronics, microwave engineering, photonics, and even ray optics. So with that, I'd like to come to the outline of my talk. So today I'd like to tell you about my work in moving this frequency band into the quantum playground. The project I will concentrate on today is this hybrid system for interfacing, interconversion and entanglement of millimeter wave and optical photons using Rydberg atoms as mediators. This project has led me to come up with this really flexible and interesting high Q millimeter wave cavity for hybrid experiments that I will go into details. I will also tell you how search for this cavity led to explorations of other linear devices such as photonic crystals and coaxial cavity at 100 gigahertz. And finally, some of the recent work we've done on exploring possibility of doing using twisted millimeter wave cavities for exotic photonic states, and finally building circuit QED platform in millimeter wave frequency band. So for example, we've recently made a 2D nonlinear resonator and have shown 4-way parametric amplification at 100 gigahertz. So these are projects that I've worked on during my PhD, so it's only a few years of work, but hopefully through today's talk, I can show you the possibilities that millimeter waves have in quantum technology, and get you excited about a few projects that we're working on right now. Okay, so as I said, I will spend most of my time talking about our hybrid experiment for interfacing millimeter wave and optical photons. But to really introduce our experiment, I have to talk a little bit about a giant effort in our field, and many of you are involved in this effort as well, of interconverting microwave and optical photons. So this field has been really hot recently, and there is a reason. For every quantum platform that works with light has a natural frequency regime, which comes with its advantages and disadvantages. So microwave frequencies, for example, are easily manipulated with superconducting circuits. The main advantage came from Josephson junction and led to development of really high fidelity single and 2 qubit gates. And as long as the system is kept at millikelvin temperatures, this is a very promising and mature platform, and one of the leading platforms towards the realization of quantum computers. On the other hand, optical photons are easily and naturally interface with atoms. And because of their high frequencies, they can act as robust long-distance quantum buses of information. And they have a benefit of working and being in the quantum or a few body regime at room temperatures. So, of course, you could already see that if we do want to build extended quantum networks, or quantum internet, if you will, we would need some hybrid quantum repeaters and quantum converters that we use in classical everyday life all the time. Now, of course, the problem comes down to the fact that, as Maxwell told us, photons don't interact with each other naturally. So if you shine 2 laser beams through, they just pass and don't care about each other. In other words, there's no such thing as lightsabers, sadly. So what we need is an effective medium. And this medium needs to have both optical and microwave properties. And most importantly, it needs to have an ability to change its optical property from a single microwave photon and vice versa. So you could see how that is quite a challenging technological task, because what you need is a system to change its properties from 2 particles that are 5 orders of magnitude different from each other. So for optical photons and microwave photons. So, and this needs to happen in a coherent way while preserving low noise and a low heat environment. Okay, so there are a lot of platforms, and there's a lot of effort, as I mentioned, in this field. The main 2 I'm going to talk about is the optomechanical systems, which again, many of you are familiar with. So in these systems, the medium, this effective medium that has both optical and microwave properties, is a membrane that directly couples to radiation through its vibrations. So the great advantage of a membrane is that you can, it's easy to couple to it because it's a macroscopic body. But the disadvantages come from the fact that because it's a macroscopic body, finding something that has a high nonlinearity per excitation or high effect per single photon is really difficult. So a lot of the times the systems need to be driven really hard, which could lead to heating and noise. On the other hand, we have atomic effort. And then in this platform, we have an opposite problem. So atom is small. So with a single optical photon or single microwave photon, you can really make a big change in its optical or microwave properties. However, because atom is small, it's really difficult to couple to it strongly, which means you really need to engineer the coupling or, improve the cooperativity, where cooperativity, what we call, is the interaction strength over the coherence time. So here where I would like to reintroduce my system for interconverting millimeter wave and optical photons using Rydberg atoms. Of course, as I mentioned before, we're not converting microwaves to optical, we're converting millimeter waves to optical for many reasons I will describe later. So that brings down the difference in order of magnitude from 5 to 3. So that's nice. And the other thing I would really want to impress upon you is how Rydberg atoms are really ideal qubits at both millimeter wave and optical frequencies, and how they are a fantastic interaction medium for these disparate frequencies. So with that, let's talk about our experiment and our proposal for the interconversion and entanglement. So first thing, as I mentioned, for these systems, we need medium. In our system, the medium is a Rydberg atom. You can think of Rydberg atom as a just really highly excited atom. So you take the valence electron and you excite it really high up to really high N, sometimes even close to ionization. So when you take the valence electron really far from the center, your effective dipole moment goes up. So Rydberg atoms interact with light much stronger than their less excited neutral atom counterparts. In fact, for our system, we specifically use Rydberg states of rubidium-85 atoms. So I'm showing you here a very simplified energy spectrum that is relevant for our setup. So we start on the ground level, which is a stable state of the atom, 5s. Here the atom can absorb 780 photon, which is our optical photon, and gets promoted to the excited atomic state. Then blue light transfers us into a Rydberg state, where the atom has access to Rydberg-Rydberg transition, which has a splitting of 100 gigahertz or 3 millimeters. So this is how we give millimeters and optical frequencies ability to talk to each other through the medium, which is an atom. Now, there are other requirements that need to happen. As I mentioned before, cooperativity is really important. Higher the cooperativity, more efficient is the interconversion. So in order to have high interactions or high cooperativity, on the optical side, we put optical photons inside of Fabry-Perot cavity, which means they'll live longer than they would in free space. And we load many atoms inside of this cavity, which means our interaction strength goes up with the square root of n of atoms. On the millimeter wave side, we put our millimeter wave photons in a tightly confined superconducting cavity where they live for a very long time. And we interact those millimeter wave photons with the Rydberg state of atom. And as I mentioned before, Rydberg state of atom has a bigger effective dipole moment. And as I will show you later, really strong, really high cooperativity between a single millimeter wave and single Rydberg atom. Of course, for these two to talk, both of these cavities need to be located in the same place, which means our hybrid setup requires a very, in some sense, bizarre hybrid cavity, which, it has a low mode volume because we want to, again, put photons in as localized place as possible to increase the coupling strength. We want them to be low loss because we would like photons to be around long enough for the interactions to happen. And the strange, a little strange requirement that we have for this hybrid cavity is that we need line of sight access to the photons because we would like to load atoms inside of this hybrid cavity. And we also, once the atoms are loaded, we would need to access these atoms using different laser beams, such as 780, blue, and as I will show you in a bit, UV light. So I'm gonna now hop a little bit in the future and say, let's imagine we've come up with this magical device, we've built our system. What would we measure first in our setup? So before we do that, let me tell you where we are in a parameter space. So on the optical side, we have a single optical photon, a single atom G interaction. The kappa optical is the loss of the optical cavity. And so we have an optical finesse of 2000 of a Faber Pro. That's where our atoms live. So for a single atom cooperativity is about 1. It's a bit less than 1. So this is pretty normal for atomic systems because the dipole interaction is not that strong. So we overcome this challenge by putting many atoms inside of optical cavity, and we get an enhancement from collective state of square root n, where n is a number of atoms in our cavity. So with that, our optical cooperativity becomes about 100. Now, when we go from a single atom to a collective state of atoms, we gain in cooperativity, but we lose a very important thing, and that is the intrinsic nonlinearity of a single atom. As we know, atom is not a harmonic oscillator. The energy splittings are different, so you can't excite the same state twice because of its nonlinearity. So when you go into collective atom picture, you lose this nonlinearity. But for our system, we gain it back through the Rydberg interaction in the millimeter wave side. So on the millimeter wave side, we have a stronger interaction for single millimeter wave in the Rydberg state. We also have extremely low mode volume below lambda Q. And our cavity has a Q of tens of millions at 1 Kelvin. So that gives us a single Rydberg atom and single millimeter wave photon cooperativity of above 20,000, which is extremely impressive for a cold atom system. And again, we get that purely from the fact that dipole moment of Rydberg atoms is really large, and our cavity confines millimeter wave photons to small volumes really tightly. So with that, the first thing we would like to see is this nonlinearity. Those who work in photonics and nonlinear system would be able to identify this parallels in their system. So first thing we would like to do is to measure transmission of our optical cavity in this hybrid situation, and we'll get a Lorentzian transmission as you would expect. Then we would load atoms inside of the cavity here, and we would expect to see vacuum Rabi splitting, and where the difference between these peaks would be proportional to the single atom G multiplied by square root of number of atoms. Then we would shine the blue light, and we would get the electromagnetically induced transparency at zero detuning. And if that Rydberg state is strongly coupled, or the Rydberg transition is strongly resonantly coupled to this millimeter wave cavity, even if there are no millimeter wave photons inside of that cavity, we would get a splitting of that EIT peak. We could also just count photons inside of our millimeter wave cavity. So the splitting goes up with the square root of n of millimeter wave photons. So by measuring the distance between these peaks, we could, through just looking through the transmission of the optical cavity, see how many millimeter wave photons we have. And of course, as any respectful nonlinear experiment would do, we would also like to measure G2 or a second order correlation function and see the non-classical signature of G2 of going below 1, which in our system would mean that we cannot send in or therefore detect 2 optical photons at the same time, because the presence of 1 photon due to nonlinearity will shift the system, making it opaque to the second photon. Okay, so that's a little cartoon of what I think it looks like when the millimeter wave photons push out optical photons out of the cavity. So optical photons are, in this case, are these red balls going through the system, they're yellow atoms inside, and whenever there's a millimeter wave photon present in the cavity, they shift the system due to nonlinearity and push the optical photons out. And of course, the motivation of this experiment comes from interconversion between optical and millimeter wave photons. For that, we would like to add I guess in this case, a 4th light or a 3rd laser, which we would use 297 UV laser that couples the lower Rydberg state back to the ground state. In this way, we have this unitary closed loop between 780 and millimeter wave photon, where we can transfer information fully from optical to millimeter wave and back without loss of information. Of course, for this to happen, we need energy conservation and also phase matching or momentum conservation, because if you do mismatch the momenta in this loop, you will end up giving momentum to atoms, which means you are entangling the information in your optical field or a light field into an atomic sample, which means you cannot state that you've converted all of the quantum information from one frequency regime to another, because you can't trace out the atomic part of your system. So with that, I just wanted to show you what our interaction Hamiltonian looks like in the system. This is just as a reference. We start with this complicated many parts interaction Hamiltonian. This is written in a single excitation manifold, and the sigma operators are collective states in collective transitions in our system for atoms, and a millimeter wave and a optical are corresponding harmonic raising and lowering operators of light fields, both in the millimeter wave cavity and optical cavity respectively. So of course, we can linearize the system, and no, of course, it's not trivial. We can linearize the system and get the familiar beam splitter relation between a optical and a millimeter wave, and with some effective conversion coefficient, and with the pretty reasonable parameter space, much less stringent than what we're actually operating with right now in the nonlinear regime. We get at 75% conversion efficiency, we approximate and expect a few megahertz of bandwidth, which is quite good for these conversion experiments. Okay, so with that, I'm going to jump into experimental realization. If people have questions, please do ask. Otherwise, I will just move on into how we accomplish this and how we build the setup. Agneta, should I go ahead or?
Yeah, I guess
Yeah.
I said it at the beginning. If anyone has questions, you can either put them in the chat box and I'll read them, or you can unmute yourselves and ask. But it looks like there's no questions in the chat box now. So yeah, I guess you can just keep going.
Awesome. Okay, great. So before I show you what the experiment looks like in real life, I will, as said, a tradition already, show you a cartoon of it. So this is a kind of an experimental sequence inside of our setup. So I will talk you through slowly through this video, and then we'll watch it one more time. So we start from a grating MOT. For those who are unfamiliar, MOT is a magneto-optical trap that traps and cools atoms in a UHV environment using electromagnetic fields. So we start from a single beam MOT. These yellow balls are rubidium atoms. So we shine single beam, it reflects off this chip in a tetrahedral manner, and at the centroid of the tetrahedron, we create zero radiation pressure where atoms are trapped and cool down. So we trap atoms in this mode. Then once they're cooled, we lower them into an optical lattice, which we use as a conveyor belt. An optical lattice is basically we created by shining two opposing lasers of the same frequency, which when they overlap, they create a standing wave. And atoms like to live at the bottom of the standing wave. Now, if you slowly change the frequency of one of the laser beams, your standing wave pattern changes. And if you do it adiabatically, or if you do it slowly, that standing wave pattern drags atoms with them. So if you change the frequency in the right direction, you can move atomic cloud wherever you need to be. And for us, we trap atoms above our cavity, and then we lower them down for about 7 centimeters down into our hybrid setup. Okay, so we'll load them in optical lattice, transfer them down into this hybrid cavity, where here, these atoms interact with both optical and millimeter wave photons. Okay, so let's watch it one more time. So we have atomic source, it emits atoms, we trap it, we cool it, we load it in optical lattice, and we transfer it inside of this hybrid setup. And where they interact with these red balls, which are optical frequencies, then there's the EIT blue beam on, and millimeter wave frequencies are fed through the waveguide. Okay, awesome. So now let's talk about the device, the hybrid cavity that made this experiment possible. So as I mentioned, it needs to have, the millimeter wave cavity needs to have really low mode volume, low loss, line of sight access for atoms and laser beams, and an ability to somehow hybridize with a Fabry-Perot cavity and have the wastes of the both modes to be at the same location where atoms could be loaded into. So whenever we make a millimeter wave or microwave cavity, for that fact, or any cavity, any resonator, we always think about carving out a volume. If we're making it for photons to live in a vacuum or air, we carve out a volume inside of stock of material. So now, of course, because we live in a three-dimensional world and there's no fourth dimension we can access, we end up breaking the surface of our stock material. And by that, I mean, we have to make our cavities out of 2 pieces or 3 pieces and then fasten them together. Unfortunately, when we do that, even though we can create really good seals, when majority of time photons still leak out. So sometimes you can work with symmetries and modes and surface currents to really design the leak to be as little as possible, but it always comes down to, it always ends up being the bottleneck for the quality factors of these cavities. So what we want to do is somehow create a transparent box for photons out of which they can't escape, but we can still access whatever is happening on the inside, as this cat is doing in this cage. And the idea behind the cavity and how it worked out is actually not that different from this sad cat. So what we ended up doing, and what I ended up realizing, is that when you take a piece of material and you drill a tube, let's say an evanescent waveguide. Let's say you want to create an evanescent waveguide for 100 gigahertz. That means you drill a tube with the diameter less than half of the wavelength or quarter of the wavelength. For that waveguide, 100 gigahertz frequencies just bounce off the surface of the stock and don't go inside. Now, if you take 2 of these evanescent waveguides and overlap them in any way but the collinear, when they just overlap, with any intersection that don't align, they creates this enlarged volume at the intersection. Another way of saying this, that any intersection of 2 evanescent waveguides has a mode, because the diameter of the intersection always ends up being bigger than the diameter of the waveguide itself. So this was a really simple idea. I got really excited when I realized this, and then I designed a bunch of different cavities, and basically come to the conclusion that you only, for no matter how many N of evanescent waveguides you need, and directions and length, you can always create a cavity with a given frequency, polarization, and even create lattices of such resonators. So the first thing I was thinking about, why don't we just make these cavities for all frequencies, since they are so easy to make, they're seamless, and you are in control of the quality factors and the coupling and the frequencies. And of course, these are just a reminder, these are in 3D. So then the answer was actually kind of simple, is because if you try to make these cavities at 5 gigahertz or 1 gigahertz, this cavity ends up being really beefy. It's just the length scale. Now at millimeter wave frequencies, which is 10 times smaller, each of these cavities is about 1 centimeter cube for really high for really high internal Qs. So even though Maxwell equations don't have length scale, our fridges do and our setups do. So this cavity design is really kind of perfect for millimeter wave frequencies, but they are quite bulky at 100 gigahertz. At a lower microwave frequency, sorry. Okay, so I made one of these, designed it, looked at the mode structure. In fact, yes, you do have this mode, and on the inside, you can change the polarization of the field by changing angles between the tubes. So I've made the first one out of niobium and drilled the holes literally in the machine shop using drill bits and a milling machine, not even anything fancy or programmable, and etched it in a acid bath with phosphoric, nitric, and hydrofluoric acid. And at temperatures of 1 Kelvin, we got consistently quality factors of tens of million at 100 gigahertz. So this was really exciting because first of all, we weren't sure that you can get high quality factors at 100 gigahertz. So there was a Hiroshi's cavity at 50 gigahertz that was really high, but the mode volume in a Faber Pro cavity that Hiroshi had is really big. In this case, we have a really small mode volume, which means the surface participation is much higher. And for niobium, the the superconducting gap is few hundred gigahertz, which is only a few factors above the frequency that we're exciting in this resonator. So and another thing that's really important to notice in this design, so even though it ended up being a really good high quality factor millimeter wave cavity, the design also makes it really perfect for our hybrid AMO experiments. So one thing to note that one of these the evanescent waveguides could just act as a spacer for optical cavity, as I've done later. The good thing about this design is optical cavity is basically aligned automatically to the millimeter wave mode. And since millimeter wave mode is really big, even a little bit of displacement of mirrors don't really affect the alignment between the millimeter wave and optical cavity. And another great thing is all of the other waveguides, the evanescent waveguides I used to design the millimeter wave modes, now could be used for loading atoms, shining in blue light or shining in UV light. And the diameter of these waveguides can be up to 1.5 millimeters, which is well enough within the sizes we need so that we're not clipping our Gaussian laser beams with a superconductor, which is, of course, could be really harmful to the quality factor of this resonator. Okay, so with that, I was really excited to go on and try it in our AMO setup. As I mentioned, we need, for the system to work overall, we need it to be cryogenic because we need millimeter wave cavity to be superconducting. We need it to resemble at least an atomic setup, which means it has to have a lot of optical access for laser beams. It needs to be UHV, and an important point which we have worked on a lot is making it low vibration. It's a dry pulse tube, which means there are a lot of vibration in our system. But since we have this optical cavity, which is very sensitive to vibrations, we had to work really hard to manage the vibrations and improve our locking abilities. Okay, so this is a little bit of a video of building the setup from scratch. This is how I found it when I joined the lab. So we got optical tables, then we got a fridge, which is like the most exciting day. And then built this hybrid homemade 2-chamber cryogenic setup with a grating mott, built lasers. And nowadays the setup looks like this. Which is just overwhelmed with optics and a lot of copper on the inside. Okay, so I will come to this point later on about advantages and disadvantages using cryogenics for the system. Oops. Okay, so we built the system. It works. It runs. As I mentioned, we use single beam grating mode to trap our atoms. We trap up to 10⁷ rubidium-85 atoms and cool them down to 40 microkelvin. We're working right now to cooling it even further using grain molasses. That's an ongoing recent addition to the system. And we trap the mott right at 4 Kelvin environment, which I think is we actually were the first ones to do that, but I'm not entirely sure, because usually people either don't have motts in their cryostats, or if they do, they usually trap them at room temperature, and then there's a long transfer using Siemens blowers and etc. for transferring atoms into the cryogenic environment. Okay, so we cool these atoms, we load them in optical lattices, as I mentioned, and from this point, this is a picture of the mott inside of our cryostat. We lower it down inside of our hybrid cavity. So this is the cavity we've used first. This is our first iteration of the hybrid setup. This is our grating mott, that's the chip we got from Strathclyde. It's fabricated not by us, but it works really well. We're really happy with it. And this is a picture of hybrid cavity thermalized to the 4K stage using flexible braids. And this is what the system looked like when we ran the experiment the first time. And again, this is the recap of the optics, the millimeter wave circuits, This is the input and output circuitry to feed photons in and out. And finally, this is the first signals from our hybrid experiment, which I'm really excited to show you. So first iteration was a trial to see, can we actually get this cavity QED atomic system working with a superconducting cavity around. So the first thing, as I mentioned, we would want to measure the transmission of the optical cavity. This is just a Lorentzian, as you would expect. This is data. And then we'll lower in the atomic cloud, and we see the vacuum Rabi splitting, which is caused by the cloud of atoms now inside of our hybrid system. Then we turn on the blue light, and yes, in fact, we do see this EIT peak in the middle. And now that finally, what we're trying to work on currently is to split the EIT peak using the millimeter wave cavity. So in order to do that, we were really excited about these results. We now put in a new hybrid cavity, which is in resonance with the Rydberg-Rydberg transition we have. And we finally put in the cryogenic millimeter wave circuit inside of our system. So we've cleaned the inside, we've put in millimeter wave circuit. You can see this is a coaxial line at 100 gigahertz. And this is what it looks like. And we have, for the first time after the upgrade, cooled down our system 3 or 4 days ago. So hopefully we'll see how it goes. So if anyone has worked with cold atoms before, this should terrify you. It definitely terrified me. So I worked with BECs before my PhD project, and this does not look like a system that would be able to maintain cold atoms experiments. But because of the cryogenics, it works really well. So you have a mott inside, we have even charcoal, tape, wires, and some Thorlam's optics on the inside of our UHV chamber. So this was a learning experience, but it worked out really well. Okay, so in the few minutes that I have left, so that was the story about our hybrid experiment. So as I said, currently we're trying to see the interaction between optical and millimeter wave photons. And after that, we also just ordered our UV laser. So we're hoping to set it up and see how the interconversion goes. But in the meantime, I'd like to mention a few millimeter wave only projects I worked on, and the things that got me really excited about prospects of millimeter waves in quantum technology in the future. So I've made, aside from the cavity that I showed you, the seamless cavity, I've made a bunch of other linear devices. For example, I've machined and fabricated these photonic crystals, which basically you can think about it as an inside-out version of a photonic, optical photonic crystal made of gallium arsenide. But in this case, you have a top and a bottom, and the boundary conditions are vacuum to superconductor instead of being gallium arsenide to vacuum. And because we'd like to have our millimeter wave photons live in a vacuum if we want to load atoms in and out of it. So I think our seamless cavity is more ideal for the hybrid experiment I'm running right now. But I think these kind of photonic crystal cavities are really neat for putting chips inside. So you can make small quartz chips with the deposition that have some nonlinear elements inside, and really couple nonlinear millimeter wave devices to this photonic crystal, which has, for fabricated ones that I've measured, the best ones I got were about 40,000, which is not great in comparison, again, to the 3D version, but it's quite good for some of the 2D linear resonators. And currently, we've made a few of these photonic crystals out of just niobium. So I had really a wonderful undergrad who designed and machined this on a CNC. So I'm really excited to eventually measure it and see if we can get higher quality factors. These are some plots of the band structure we've measured. As usual for a photonic crystal, you want to create a gap and then put a defect in that gap. So it seems to be working pretty well. And finally, I also mentioned that, as someone coming from an AMO background and, from a lab full of crazy twisted cavities, one thing that crossed my mind that wouldn't be kind of cool to explore these exotic photonic manifolds or, photonic landscapes that are not geometrically trivial using millimeter wave frequencies. And the reason I've started thinking about that, because making mirrors out of metals just require programming a CNC machine. Of course, to get it to really high quality, you need to do a deposition, you need to really polish the surfaces and all that stuff. But that is required when you're really going for really high quality factors. So you can machine these mirrors in a machine shop. So this is like one of our assembled Fabric Pro cavities. This is for those who played with Fabric Pro, it's kind of cool. This is data of getting Fabric Pro cavity at millimeter wave frequency through degeneracy point. So just by tuning the length of it. So it acts as a very normal Fabric Pro. And the other advantage for twisted cavities or for non-trivial geometries for photons for these mirrors is that you can basically imprint an arbitrary phase imprint on top of these mirrors just by using machining tools. So if you want to make some non-local interactions, or if you want to make some a weird phase profile of your mode, you can just do that by kind of using the tools of metamaterials and machining different perturbations on the surfaces of these cavities. So that's the reason I got excited about using the millimeter wave cavities or twisted millimeter wave Fabric Pro cavities for this kind of mini body, maybe one day experiments. So of course, one of the biggest challenges of using metal mirrors for the twisted cavities is that you cannot image the mode shape on the inside. For those who work on optical frequencies, you can just put the CCD camera on the outside, on the other side of the cavity, and as long as you have the right lensing and coupling, you can see what mode lives on the inside of the cavity. Is it Hermit-Gauss? Is it Laguerre-Gauss? Which Hermit-Gauss mode is it? And that's really important when you're trying to create these tricky mode shapes inside of your cavity. Now, of course, one problem is metal mirrors are not semi-transparent, so you don't see anything on the other side. And another issue is that even if there were, there's no such thing as CCD camera at millimeter wave frequencies. In fact, the best CCD camera we have at millimeter wave frequencies is South Pole telescope, which is not very affordable or convenient. So you need to figure out some other ways of figuring out what kind of photon and what kind of photonic manifold lives inside of your Fabric Pro. And one thing I wanted to mention is that I've played with imaging the mode on the inside by just basically taking a dielectric thread and crossing it through the mode of the Fabric Pro inside. And if the thread is really thin, it induces loss only locally. So you can basically, if your mode looks like this, let's say it has 5 nodes, and if you have a really thin thread crossing the cavity mode across here, you should be able to count number of nodes the mode has by seeing how the finesse of the cavity changes as you're traversing the mode. So this is a very, very preliminary data of imaging it. And in fact, you can actually see the modulation and finesse. I also see the same modulation in the transmission peak. So you can see it from the width of the transmission, and you can see it from the frequency itself. Sorry, so because you have 2 effects. One is loss, and another one is just the dielectric shift of your mode. So as long as your this perturbation is not coupling the modes into each other, then you can really see and quote unquote image your mode using this tool without having to have a camera or having this semi-transparency of the cavity. Okay, so I'm running out of time, so I'd just like to mention our efforts on building a circuit QED-like platform at millimeter wave frequencies. And together with my colleague in Dave Schuster Lab, Sasha, we've made this 2D nonlinear resonator at millimeter wave frequencies and showed a first parametric amplification for superconducting nonlinear cavity at 100 gigahertz. This is what the setup looks like. So that's quite exciting. And we're continuing to explore this more circuit QED-like platform for millimeter waves and seeing what else can we do for nonlinear devices, and as well as doing more microwave and millimeter wave hybrid experiments and parametric cooling and experiments like that. And finally, I'd like to summarize. So we've talked today about why millimeter wave band is a promising platform for quantum technology. I've told you a little bit about our hybrid millimeter wave and optical system and how we use Rydberg atoms to interact between optical and millimeter wave frequencies and our recent progress on it. And I also mentioned a few linear and nonlinear devices that I've worked on together with my colleagues, both in Simon Lab and Schuster Lab. And of course, I'd like to thank both of my labs. I am very lucky to have two awesome PIs and two great labs to work with. Both John and Dave have managed to encourage and guide me on this big project that I worked on, and also really entertain my little obsessions on the side with millimeter wave frequencies and the devices. And of course, my lab mates, Mark Stone, who we've worked on this big hybrid setup since the beginning. I was the first graduate student in lab, and he came a year later. Now we have Ash, who's a great postdoc, Lavinia, our new graduate student, and as I mentioned before, Sasha, who was essential for a lot of our circuit KD efforts at millimeter wave frequency. With that, thank you so much for your attention, and I'm really happy to take any questions you have. Thanks.
Thanks, Aziza, for the great talk. I will stop the recording now, and then I guess we can do questions for a few minutes.